Right. So I was doing this table. No, sorry. I was doing the classifier. No, decision tree. Yeah. It's a donation data set. And I didn't do the stat explorer, probably because of the time. Yeah, right. So typically with a new data set, with a new project, you would explore the data to review missing values and other distribution issues. In this data set, there are quite some missing values if you look at the Stats Explorer results. I will demo some of the other nodes that fix the missing value case, that impute the values when I talk about the regression. Here, here it's kind of a deliberate decision not to fix those missing values, because decision tree is very good at handling missing values. It doesn't automatically impute those. It doesn't automatically calculate values for the missing, but it does have a good mechanism to run the algorithm when treating the missing values as a special case. So it doesn't eliminate all the cases with missing values in those variables. So that's different from regression, where when you have a missing value in a case, that if that variable is included in the algorithm, as included as one of the variable in regression, then that entire case will be ignored, because for regression it doesn't deal with it automatically. It doesn't have a mechanism to do that. You would have to impute it or replace the value of missing in some way before you do the regression. For decision trees, it deal with that. I don't know if you remember that when I do the splitting, the way, how do you go back to the interactive tree? It's an interactive option on the left. So I was growing tree by one split. Then I got two nodes. For the first split, if you can redo it again. If you do split the node, you get when you do this, you get a list of split decision alternatives, and if you zoom in to edit the rule, you can see how SAS deals with missing values. If you don't treat missing value as a separate branch, then it will typically be included in the sort of as an infinite value. The missing value is treated as an infinite value, so that will be included in branch 2, larger than 2.5, including the missing. But you can also do this. Treat the missing value as a separate case for this particular variable, then SAS will recalculate the log worth for the variable, and basically separate them into 3 branches instead of 2. So you can do that, and you can demonstrate that, right? Sorry, too loud. Right, so now you see 3 branches, but the third branch with missing value is very small, very thin. It may not even have any cases in it. But again, decision tree has this capability to do that. So even if you don't impute the missing values, sometimes being missing for a key variable also indicate a lot about the outcome, right? So having the ability is good here. This ability is not available for almost any other algorithms different from trees. Trees do have this capability for different kinds of trees. So, but I'm not. So I will reset it and reverse the action. So this would be the split outcome for the first one. Then you can do the same interactively over and over to grow the tree. But when do you stop? Do you stop when the leaf is smaller than 100 in size? Do you stop when the accuracy rate is higher than 80%? Or do you stop when you get a clean leaf node? That might be many steps ahead. So the stopping point is one decision that you will have to make. There's no perfect decision here. The mentality to do that is that you try to grow the tree as much as you think it's definitely too much, it's definitely overfitting, then you can stop, right? But still, when do you stop? In SAS, there's a default setting. It's set at depth of 6. So it tries to grow every branch until it reaches the 6th depth, and it stops growing. But this rule is also governed by other rules. Like you can't have, you need to have a minimum number of cases in the node before it can be split, right? The minimal size may be 10. So if after two splits, the leaf node only has 10 cases, then you cannot split anymore because there are too few cases there. Any more splitting, you are adding much more errors into the split because it's too small of a sample. Here, you have many cases, so it can keep growing, right? So with those defaults, I didn't change the default. With those defaults, you can choose the automatic mode instead of doing the babysitting mode, right? So manual mode would be a babysitting. You're splitting manually, one by one. So you're babysitting it. You can change the rule. You can edit the rule, the splitting threshold. But I don't see any reason to tamper with it. I would simply automatically grow it. So you can train the node is when it try to train it to the maximal size governed by the rules. So if you do that, it will grow to a depth of 6 as much as possible. If you see the longest path, 1, 2, 3, 4, 5, 6, 7. So maybe 7 is the default. Yeah, and after this point, it doesn't grow anymore. Let's take a look at the sizes of these leaf nodes. So here you can see that, but this one is also reaching the maximum depth. So either way, it's not going to split. For this node, there's only nine points in training set, and the separation on training is very clear. 9 points, all of them have an outcome of 1, which is donation. But on validation, it's 50-50. So drastic differences across across the partitions. That means here the results are not very reliable, and you have big variations across the partitions, right? So this is a signal for overfitting regions. But this is fine. This is happening to this node. You don't try to eliminate this node at this point. There's a better mechanism to do that. Right, is by using the more of a systematic approach. If you try to delete this node, you can do that, but deleting this node would result in deleting this node too, right? Because you will eliminate this split altogether, and this one becomes a leaf node. Doing that has a consequence of you would have lost this decision node. Which is quite consistent across the two partitions, and it has high confidence. 62% of the cases are have a result of 0, non-donation, and the number of cases are quite substantial, 300 something, and the confidence is consistent across the two partitions. So this one doesn't have any signal for overfitting. So that's good. And it does have a substantial part, not substantial, maybe 3% of the entire data set, which is not small, again, 5%. So at this stage, I recommend not manually delete, which is the word prune for. Pruning the tree means to cut it back, to prune it, to reduce the complexity of the tree, is to try to improve the optimization of the tree in terms of performance. At this stage, it's growing. So when you grow a tree, you try to grow it to the point that it's definitely reaching an overfitting region. You want to be deep into the overfitting region, but not too deep. Any deeper, you're wasting time. But you want to make sure it's sufficiently overfitting. And so if after you have grown the tree to the maximum, you take a look, at these leaf nodes and heuristically, without calculating too much, but get a feel of how much overfitting is there. See, for here it's still fine. For this, and interestingly, even when it's splitting into two leaf nodes, it doesn't guarantee that the prediction would be different, even if it splits, right? So you would assume automatically that the prediction on the left leaf node will be different from the prediction on the right leaf node because it's a split. But again, if you look at it, it's on the left side leaf node 76. The majority are non-donors. You would predict non-donation. And it's consistent. The conclusion is consistent across the two partitions. On the right split, also the majority is non-donors. So this split didn't have any ability to differentiate donors from non-donors. The conclusion would be the same even after the split. And before the split, the conclusion would be the same. So this node probably isn't necessary, at this stage, right? Or it may be necessary if you look at the confidences. So this would mean that it's unclear to look at this point. Then it's possible that the tree is in a staggering stage where the performance is not increasing, but the complexity is increasing, right? That might be in the overfitting region. So there isn't much. I think all of these are me talking from my experience. There's not many golden rules to standardize here. Basically, I'm trying to say is that you grow a tree to a sufficient size and complexity. And there are signs in the leaf nodes that will indicate if you have already grown a tree too big to the extent that some of these splits might not be clear, right? But the splitting operated according to the same rule. You know, whenever a split would be happen, I can split, maybe not when I see, I can probably split here even if the program didn't split. So when I try to split, it still look at all the alternative split decisions that the algorithm can use, right? It basically it searched over all the variables, input variables, and all the levels of those variables, and simulate a split, and then it calculates the value of that split, and demonstrate the value here and make a ranking. So if you take a look, any of these split possibilities doesn't provide any value here. It doesn't separate them. It could be because all the values here, all the data points in this node share the exact same values of these variables. So that's why it couldn't slip. It couldn't split. You try to split, then you would have only gotten one partition, one group, because they cannot be differentiated. They are exactly the same on these input values. You know, but it's possible, right? It's possible when you look at the entire population of the U.S., it will be easy to identify 50 people with exactly same information that you have collected. Same age, same gender, same name, same income, our family, history, maybe not the same address, but any other things that could be potentially the same might be the same. Then you cannot split them in these cases, so they would have to be in one group. So in these cases, you could not split. Anyway, so the growth of the tree the growth of the tree is done. This is what we call maximal tree. Is a tree that you are quite confident that is sufficiently large enough that it's overfitting. To demonstrate the differences, and by following the PDF tutorial, I will freeze the tree so that I will not allow SAS to make any changes to optimize the tree. So here I would change it to frozen tree, and after that, you probably don't even have to train it because in the interactive steps it's already trained. So this is a maximal tree and it's frozen. It cannot be modified unless you modify this option, right? So we'll leave it there, and we'll train some other trees, and let SAS do all the job, and let SAS optimize the best tree for you. So going back to the slides, I've talked about tree, those nodes, branch, and grow, and split. Grow is meaning splitting a tree. Split metric is the log worth, the ranking of the potential split decision rules. A decision rule is, how to split the data based on a particular variable and a particular level.
Okay, so where we can change the default values for the split, you said?
For like depth?
Yeah.
Great question. It's all under the properties. So if you look under splitting rule, it's not allowing me to change because I froze a tree. But maximum depth, you can change it to something else. You know, if you are not confident the tree is complex enough, you can modify it to 10. It will try to grow as much as possible. If there's a possibility to split, you can change it smaller as well. Most of these, well, all of these properties govern the way it splits. Number of branches, currently it's restricting to 2, but you can, you know, allow more branches each time. It simply adds more complexities, right? Adds more flexibilities. Significance level also govern whether a split could happen, right? Significance level is the p-value, is p-value in log of p. The log p is the log of the p. For here, the 0.2 is setting a minimum value the p can be before a split can happen. So that's why when log p is 0, that means the p is the p is 1. The p is simply, it cannot be larger. It's not significant anymore. So with p being 1, it cannot split. Right? And there are other options here. Is that good? Yeah. Right. So next I'll talk about prune a tree. But before I talk about that, I'll talk a little about the homework. In the homework, you will use the telecommunication data set, the churn data set, to grow 2 trees, I think, based on 2 metric. After you grow a tree, the question will ask you to extract the decision rules and make it a table. The decision rule will be similar to what's shown here. You know, a decision rule is describing a split and how the split happens. You know, if then else, the condition, right? If the variable is larger than something, then it goes to left or right. If otherwise, then it goes to the other side. This is, and then you will need to calculate the number of cases that went into one side, and the confidence of those cases, the confidence of prediction in that branch, in that leaf, in that branch, given the split. So you can extract all the information after you have grown a tree from SAS very quickly, but you'll get a lot of information. So let me show you. You can go to results. So it's the same tree. After you have grown a tree and run the node, you can go to View, Node Rules. It gives you a lot of information here. Every section is a leaf node, meaning one of the nodes at the bottom. You know, it doesn't have to be the very bottom ones. It simply has to be a leaf node, which is the end of each branch. Right? That makes sense? It doesn't split anymore. So each leaf node rule describes the entire chain of decisions that from the root node leading up to the leaf node. So we can take an example. Node 22, and I need to make it large. And the node ID is noted on each of the node. For node 22, I need to find that node. Somewhere. It's here, so it's easier, one of the easier one. Node 22, the node rules describes the path from the root node all the way up to this node, right? So it describes the first split is gift count 36 month. If maybe there's something else. If status category is 1, and so it describes it up reverse order. It describes the down the closest split first. If the status category is one of these levels, and if the median home income is larger than this value or missing, and the last one would be the first split, is if the gift count 36 is smaller than 2.5. Then all of those cases that satisfy these conditions simultaneously will end up in this node 22, right? So this is one decision rule. One decision rule that you will write. You will write to one row of the table in the homework, and then you would do the same for all the, end nodes. Here there may be 20 something, so there are quite a lot. For the particular homework question, it may not be the maximal tree, so it may be one of the optimal tree. So it's fewer nodes. It doesn't have to be this long, but it will be the same format, right? So all of these are text you can copy and paste, but it doesn't form a table automatically, and not every information here is what you need. For instance, you need for the decision rule, you need the if-else condition. So you can copy these. The if condition, they're almost ready. You probably rearrange them into one row or something like that, and you will be good for that. Then, what decision do you make, right? What prediction do you make? Then you need to look at the statistics, the confidence for either decision, and make a pick. So which one is a majority of the cases? And this is describing the training data set result. In this case, the outcome for target being 1 is 60%, and that's a majority. So in this case, you would the then outcome consequence result will be donation decision in this case. So your consequent result would be donation or donor result, right? Or you can say simply equal 1, but you want to make sure you have conveyed that, what's the target? Target is the donation, not simply 1 and 0, meaningless 1 and 0, right? So you can't simply copy and paste everything over there. It won't make sense. You'll have to extract some information here. The third piece of information is number of cases that is in its node. And here the result tells you it's 147. It's a third cell. Number of cases. And confidence. Confidence is the confidence in predicting that particular outcome. Here it's 60%. Right. So that would be complete for one decision rule. After you describe one side of the split, you don't have to describe the other side. But it's almost complete information for if you understand the decision rules.
Do we have to do it for every branch?
Yes, yeah, right. So you would imagine that the confidence column would be always over 50%, right? Because that's why it's confidence. Any other questions? You will do 2 tables for the homework for 2 decision trees. So most of the graph are under view model after you go into the results.
Decision tree means like for 2 different sets?
For 2 different models, same data set but 2 models. I'll explain why that will happen, because there are different ways to select the optimal model. Yeah. All right. Now I will talk about pruning the tree. Of course, you can do the babysitting way, right? You can prune. Can you prune? Let's see. Can you prune? Oh, yeah. Probably I froze the tree, so I cannot prune it here. So let me do a second tree. And I'll rename this tree as the Maximal Tree. And the second tree would be, let's see, best classification tree. And to start out, I'll also do interactive, just to show how to do the pruning. Does it make sense? The growing tree part, right? And this is not yet to the maximal tree, but I can prune the one level up. If I prune that level, then the split will be gone, right? So that with every prune, you lose not only one node, but you lose 2 nodes. You're going to have to reduce the level. Anyway, so now let me train the tree automatically, and then it's the same tree. Go back. Right. So far, when growing the tree, it uses the log p, the log worth metric to grow the tree, right? It only considers that, and under the restriction of the other meta rules about the maximal tree, it can't grow under certain conditions, so it won't grow. Otherwise, if it can grow, it will grow by selecting the decision rule that gives the maximal log worth, right? So it grows like that until it reaches the maximal tree. So now let's take a look at the pruning process. In the splitting rule, you do have some option to change the criteria, by which the SAS will rank different alternatives and choose the highest one. Previously we used the log worth, which is the probability, the log p. P is from the chi-square test, so that's why this is probability of chi-square. For nominal target, we're doing a nominal target now, right? It's a donation, 1 or 0. But you do have other choices. You can do entropy, you can do Gini. Now entropy Entropy is talked about in the other book, the the other book by Provost. So that's the optional reading. If you want to do that, you can take a look. Entropy is somewhat more intuitive. Entropy, you can see clearly how entropy changes when the class composition changes from 0 to 1. It's very intuitive. But as with any other metric, there's no definite advantage or disadvantage. They just give you different flavors and different advantage under different cases. So it's good that you have different options here. You can change things and give you more rooms to train alternative models, and then you can compare to select the optimal model. So here, that's it. All the other parameters govern the maximal tree. But think about the objective of training a machine learning. We want to predict the donation behavior, right? We want our model to be able to predict donation with least amount of error, right? When I say error, it's a misclassification for a simpler scenario, right? There may be other decisions involved in terms of weights of different decisions, but for now, let's say correct classification is good, incorrect classification is bad, and false positive and false negative are equally bad. For now, let's assume that. So in that scenario, we would choose the model that has the lowest misclassification error, which means it has highest accuracy. But so far, we haven't done that yet. Right? When we grow the tree, we didn't take into account the model's misclassification error. We simply look at all the possible splitting alternatives calculated by using the chi-square test, right? And we grow the tree over and over, and make the tree more complex. And that's the only thing we did. We haven't taken a look at the performance yet. So that's a metric that you will use to select the best tree. Now, if you imagine the maximal tree, if you cut anything away from that tree, it becomes a different tree. It will lead to somewhat different overall performance, right? Because some splitting is taken away, and those part will change the overall results, but maybe not for a significant amount. But if you change a lot, you prune this part, but you decide to continue to grow the other part, it becomes a different tree. And the overall performance may change. So it gives you many, with the maximal tree, you have opportunity to reshape it into subtrees, different subtrees. You have many possibilities, right? Imagine that there are 10 branches. You can cut here or there. There are many alternatives that give you a different tree. With a maximal tree, you definitely need to cut it back, but where do you cut? It's hard to decide. You can cut and get feedback and adjust. That's a babysitting approach. It takes a lot of time. It doesn't lead to the optimal solution. So what you want is do a systematic search. A systematic search will exhaust every possibility in pruning the tree, one level at a time. And then you compare the thousands models in the end and see which one performs the best using the test data set.
Is it faster than the other approach? As the babysitter?
In terms of finding the optimal solution, yeah, of course. Yeah. But if you program it and let the computer do it, maybe the same. But you cannot do the babysitting approach manually. It doesn't work. But either way, a systematic approach, a systematic pruning approach will be is the way SAS implemented. So let me show you the result of that. So I only grown a tree that so far, and the SAS ran to grow the maximal tree and calculate the node statistics. It hasn't pruned yet. So what I'm going to do next will let SAS do the pruning step, and we'll see how fast that goes. You know, I will select a metric here by. So let's see. Use priors? No, we're treating false positive and false negative the same. We're not assigning different weights. Exhaustive 5,000. So 5,000 different is the maximum number of searches or alternative trees that the SAS will search. 5,000 would be sufficient for this case. And then subtree is where SAS optimize and choose the best tree. But how does it choose? You know, which metric does it compare the different trees? Default is decision because the target variable is nominal. It chooses a decision by default. But here, decision would be no different from misclassification because we assign equal weight to different outcomes. So it will be the same result either way if you leave it as default or you choose misclassification. So I've chosen that. That's only a change of property. It didn't lead to any calculation. But when I run it, and notice this time I didn't freeze the tree. I let the SAS do the pruning search, and I have customized the criteria. Now I let it run. This is triggering the pruning process and the search and optimization. So I will show you the result, and then I will show you I will explain to you what SAS has gone through. So it'll only take maybe 5 seconds, right? There's a graph that's important. The graph is the overfitting graph that doesn't automatically show, so you will have to call it. It's called subtree assessment plot. And make sure every time you look at the assessment plot, you need to make sure that the metric is the one that you designated. It doesn't automatically choose it, which is stupid, but I guess SAS assume you're intelligent, so it doesn't so it doesn't do things for you too much. So I chose the misclassification rate. All right, so what does it do? The number of leaves indicates the complexity, right? Whenever you see the overfitting graph, the x-axis is always the complexity, but it's different. It's different parameter for different models. For regression, it's number of coefficients. For trees, it's the number of leaf nodes, right? Another way to represent complexity. The maximal tree may have close to 57 leaf nodes, right? So that would be the maximal tree at this point. That the graph can go. It can go anyway, any more complex, and the models on the left are more are simpler, right? So this would be conforming to what you expect from an overfitting graph, right? The y-axis is the error. As it started out, the accuracy is 50-50, which is the worst. Yeah, it doesn't help at all. And as you grow the tree by 1 or 2 or 3 splits, it quickly goes down to close to 40%. And then as it grows more, it increases more. You notice that the blue line continues to fall because that's the training performance. That's the training set error rate. It eventually becomes very small. It doesn't go to zero. Interestingly, for trees, it doesn't work like that. It won't account for every error in the training set, but still it goes down to significantly low. But at some point, the validation set performance will reverse and go, become increasingly bad. That's the point where the optimal tree is chosen here, right? And a line is indicated where the final optimal tree is chosen by the model automatically, and you can hover over to see how many leaves are in the final tree. I noticed that when you scroll across these number of leaves, the vertical line indicates that that's the same model, but performance is different on the two partitions. That makes sense, right? So this vertical line is indicating the same model. Its performance on training is close to 41%, but performance on validation set is 43%. The error rate. If you change it to a different metric, it still shows you the result, but it's not selecting the optimal model according to this metric, because the model wasn't selected by using this metric in the first place. That makes sense? If I had selected average square error, then this model would have been selected, right? Makes sense? Great. Okay, so SAS, it's good. SAS compared the subtrees at every level of complexity, and graphed the performance for you under both partitions, and have chosen the best tree according to a metric. That's good. That doesn't sound very intensive. It's only 60 trees. It doesn't sound a lot calculations, right? Well, let me show you what's happening in the back. It's much more than that. So yeah. Here you see that the chosen model is not the best model by SAS. That's because this is a frozen maximal tree. Let me show you that if I go into the maximal tree and I call the same graph, the assessment plot, it will select the maximal tree here, even though it's not the best tree, but I have frozen the node, so it doesn't allow SAS to pick the best one other than the frozen tree. But even that, SAS will prune the tree and then calculate all the performances and make a graph for you. Anyway, going back. Pruning. So what happens when it's split and when it prune? Using two variables as a demonstration, the data will look like this. The color of the points will indicate the target variable, Right, there are two colors. X1 and X2 are two input variables. So if you do splits here, it's basically cutting areas on this plane by using rectangles, right? So let's say the tree has been grown, and the first split is using X2. So X2 is here using a level of 0.6, so somewhere close to here. Then it will, draw a horizontal line. Everything above it will be assigned, it will be split into the right branch. Everything below that will be split to the left branch. And then it uses X1. X1 is making vertical lines. Is it further cutting the plane, right? But the two split level on the upper plane and lower plane can be different because it's under two branches. It can be completely different. If we focus on this point, so the point has x2 as 0.7 and x1 as 0.3. By the first split, it will be included in this branch. By the second split, it will be included into this branch. So it will be something like that, right? And then based on the points in that region is like that. Based on the points in that region and based on the outcomes, the 70% of the points has green, right? So the confidence will be green, and the prediction will be confidence for green is 70%, and the prediction will be green for this point, even if this point is actually white. But prediction has to be applied to all the points in this partition on this split. But for the other leaves, it will make predictions based on the confidence, right, and based on the outcome. So if you can imagine, decision trees are basically cutting boards in the higher dimensional space, cutting boards, cubes, all over. And it can zoom into a very particular cube and has a prediction that's the same as some other cube in other spaces, right? They can have the same outcome, but the path that they went through is very different. So that's how decision trees work. And in this way, the model is not linear, right? The influence that one variable has, this variable x1, has influences at different points by different levels. So sometimes that variable is used to split based on one level to make predictions separately. At another branch, another level of that variable is used to split the sample, to split the data and make other predictions. So the relationship between a variable, its values, and the outcome is not linear. It can be very different, according to the specific sections. So that's how, in the nonlinear, phenomenons where the variables don't exert linear effects or linear correlations, linear relationships with the outcome, decision tree will be better because it takes the specific level into consideration.
How do you draw a conclusion how accurate the leaves are, or in comparisons to each other, the percentage?
At the leaf level,
yeah, I guess
the percentage is the confidence, right? The higher the confidence is, as long as it's not overfitting, then it's considered a good split, high confidence split, clean split.
That the data is correct or accurate?
Well, no, the model
The model
is on the right track. Yeah. But overall, you will have to look at the pruning result. This is splitting, right? So this is a visual demonstration of the split. Now, after you have a maximal tree, you have a big tree. After going through different ways of cutting, then you need to prune it. I think, I'm not going to repeat it. I think I've talked about that. Then the pruning process. You take the maximal tree. Let's say now you have grown a tree that has 6 steps. So the longest branch has 6 nodes. It's a 6 is the number of leaf nodes. So it doesn't mean the maximal length, but the number of leaf nodes altogether in the tree. And SAS also use that to represent the complexity. So in this case, the SAS will start from the maximal tree, and these 2 tables are comparing the performances across the 2 partitions. So it starts from that and calculate the performance of that tree in training and validation set, and record the results, and then start pruning. By pruning, it removes a split. By removing a split, it removes 1 leaf node. Why does it remove only 1 leaf node? It removes a split, which removes 2 leaf nodes, but then exposes that node to be a leaf node. So it subtracts 2 but adds 1 to it. So every prune removes the total number of leaf nodes by 1, right? But there are different alternatives. You can prune here, or you can prune here. There are 2 ways. That's all the ways that you can do with this maximal tree. There are 2 alternatives to prune by 1, right? You can't think of any other scenario where you can prune by 1 with this maximal tree. So that's that's all the options here, right? To examine complexity of 5. So SAS will look at all the alternatives and prune, and then calculate the performance of these 2 trees with regard to the training and validation. Right, so you have a result. Suppose the left tree is better. So SAS will remove the worst ones and only retain the best one, and record the performance and draw the graph, right? So that's a tree with 5 leaves, 5 leaf nodes. Then it moves on to 4 leaf nodes. So take a look at the possibilities. You can, with that tree, you can keep pruning, and it becomes 4 leaf nodes. You can prune this side as well, and it becomes 4 leaf nodes. But it doesn't start from this point. It starts all the way from the maximal tree. So that's why you have 3 possibilities. Starting from this point, you also have a possibility that you prune all the way 2 level up on this side and get another 4 leaf trees,
So
like
each
4 leaf
time-
things. Each time it will start from the maximal tree.
But it'll choose a different path.
It will exhaust all the paths. Yeah. So in this case, there are only 3 possibilities by going from the maximal tree, and then again, SAS will calculate the performance and retain the best one, and move on to the next pruning job. Right? Does that make sense? So the more you go up, the number of possibilities there are, and SAS will always will exhaust all the possibilities for you. So that's a lot of
So
calculation.
if you have big data, it goes on and goes
Yeah,
on.
yeah, and it doesn't stop until it reaches the simplest model. Yeah, that's it's mind-boggling sometimes. All right, then SAS will draw the graph that you see. Every model at a point is the best model of that class. Then you see two lines, and then you will pick the simplest model that has the best validation set performance. So that's how SAS, pick the optimal model. And think about the criteria that SAS select the best model. In this case, SAS doesn't use log P. It doesn't use the chi-square test. It uses the ultimate criteria that we care for. It's a misclassification rate, right? So you can almost think of the growing and the pruning process are two reverse processes, but they use slightly different metric. The pruning process is closer to the ultimate objective. The growing process uses some statistical tools to grow it. You can't use both at both paths because you quickly exhaust your possibilities. You kind of repeating the same thing if you use the same metric. This way gives you more possibilities of exploring possible trees. This for machine learning, you want to be able to search as much possibilities first, as much as possible, and then you come back and validate those models by using validation set. This is the way the machine learning tries to identify the best model. It doesn't start out by assuming too much. It simply tries to exhaust the possibilities, and then using the training set, then you use the cross-validation in the training set to validate the possibilities. The bad models will be removed automatically based on validation set. So that's the mentality here. That's it. Okay. So does that make sense? Any questions? No, good. In terms of the metric, the misclassification is quite straightforward. I think I have it here. So the misclassification rate is simply the percentage of misclassifications, right? You have a big summation of every misclassifications. When the prediction is different from the outcome on the validation set, then it's a error. It's a misclassification, right? It will be add up. So all the misclassified cases are calculated, are counted, divided by the entire sample. So that's the sample-wise misclassification rate. It's a good, benchmark performance metric to compare to.
What is IF in that?
IF is if condition. If the condition is met, then it's 1. Otherwise, it's 0. Another criteria is to compare the mean square error. And in the binary target variable case, you can also use that, and it produces somewhat different result. As you see the overfitting lines, it produced differently optimal model, because this model will optimize the average of the squared error, and it takes into account the confidence, not simply a misclassification, right? So it takes into account the sort of the precision level of each leaf node, right? Some of the leaf node has 90% confidence, and that will contribute to the reduction of mean squared error. Some of the other leaf nodes have confidence level of 55%. That's quite vague. So that will add to the mean square error of the model overall. So So using this measure will produce somewhat different tree than the misclassification rate. It doesn't always lead to a more complex tree or simpler tree. It simply leads to another tree that has the lowest mean square error. But if you have, let's see, so the mean square error, as I said, it balances the bias and variance, right? In one metric, it balances both. So to some extent, it's more preferred. Like in the general sense, it's more preferred. But it's harder to explain what happens here. You know, what does it really mean? You cannot use plain language to explain it. It simply is a mean square error. But for someone who doesn't understand equation, you try to explain it to them, it's hard to say. You know, what does that really mean? How much error is it? As versus the misclassification rate. It's very simple to explain. It's simply, you know, this is the percentage of mistakes it makes across all the sample. So that's easier to explain. Right, so it gives you different flavors. Sometimes the tree is the same. Sometimes the tree will be different under each metric. Other questions about the metric?
If they are different and like the degree of difference is pretty high, then like what's the conclusion based on that?
It's typically not high for a large sample. For a smaller sample, maybe. Yeah. I mean, if you care about if you care more about stability of the predictions, then you would prefer mean square error. Yeah, because say if you want to demonstrate how well and stable your algorithm is over time, then you probably will use it in production for quite many iterations. Then for all those iterations, you still observe the result. Then you can retrospectively calculate the performance of those predictions. Right? So you have an evaluation of those predictions. And if you compare them, if you want to maximize the stability, if you don't want your result to fluctuate too much, and to show your manager that this is a stable model, then you would prefer that one. But if the manager cares about explaining to you what it does, how does it select the best model? So maybe the upper one is easier to explain. It may have more fluctuations over time. If that's something that you don't care, then you probably can be safe on there. Anyway, it won't make a big difference. Yeah. So, break time. We'll come back at 7:32. I guess I have bad news. It's not recorded.
No.
I thought I started.
But
I clearly thought it.
right there.
Yeah. Oh, really?
Yeah. The first
Ah, it's
one.
recording.
I looked
Bad
at
news
it.
and
I'll
good
look
news.
at it right now. I wanted to make sure it was recording.
Right. So I have two trees. Let's use a tool that SAS provide for you to quickly compare the performance of all the different models that you have done. This is something that you will do later in the homeworks and in the project. After you have trained all the models, how do you select them? Within each model, SAS do provide the tool to select the best model, right? But that is under that particular setting. With the best classification tree, the metric I use is a misclassification rate. I could train a different tree, and I select the mean square error as a metric. So that becomes another tree. I'm not sure ultimately what is the best tree in making decisions. So I can use that tool to compare the different models, and I can also have neural networks. Then I use that model comparison tool to compare neural networks and trees and regressions and different models. So after you have multiple models, then you can go to assess and use model comparison. Then you can connect all the models that you want to compare to the model comparison node. And it's very critical at this point to specify the metric that you want to select the ultimate best model. It can be different from the one that you chose for a particular model, right? It can be different. And sometimes you deliberately want to do that because you want to maximize the search process, right? That's the same mentality as if under each tree, decision tree node will try to search all the possibilities and compare them and select the best one. Here, you want to generate as diverse a set of models as possible, even going with some of the specifications that may not make sense immediately, right? What I mean is that if you have a best classification tree, and if your model comparison wants to select the best misclassification model, you would assume that this one performs the best. But that may not be true because the pruning process is very complex. The training process is also very complex. So sometimes you maybe want to deliberately train another tree that selects the best mean square error and compare with this one and let the model comparison node find out which one is the best, right? So same mentality, you want to sometimes be crazy and go outside your comfort zone to train more models just for the purpose of searching for possibilities, right? So here I will select the misclassification rate, and this comparison of the different models also uses the validation data set, right? But you need to specify. Otherwise, this is another stupid side about SAS. It should simply, by default, use validation set. But the default is train. So if you leave that as unchanged, then that would be definite mistake to do, right? So make sure you change it. Model selection, change the selection table to be validate. Or sometimes you can use test, but definitely not train. If you've done that, if you leave the train there and submit your work, I would assume you didn't learn at all, right? That would be a serious mistake to do. So always check if you have specified the correct set. After that's almost the only thing that you need to change. After that, you will run it. For model comparison purposes, this table shows you which one is a better model. It will rank them based on the metric that you selected. The metric that you selected is the validation set misclassification rate. So I was comparing a best misclassification rate, best misclassification tree with the maximal tree. The the misclassification tree had slightly lower error on validation set, though that's why it's chosen. If you look at the train misclassification, it also has a lower error for some reason, just because it's less complex, right? So it has lower error on both partitions. If you look at the validation set mean square error, validation average square error, it's very close. It's not different by a large margin, but the misclassification tree still does a little bit better than the maximal tree. So it's a very clear comparison. There are other reports about the results, like ROC chart, lift chart, cumulative lift chart, and gain chart. We'll talk about these in maybe chapter 10. After we talk about regression. After we talk about neural networks, we'll talk about different tools that you can use to compare models and think about decision rules. Then we will use these charts. Any other questions about decision trees?
So in this case, maximal tree is better, right? If you say that the mean square error is low in that case.
In that case,
The
yes.
classification.
Yes, in this case, yes. Yeah, very odd, huh? Even the maximal trees. Yeah, you would think that the best classification tree would be better. But yeah. So sometimes, that's why I suggest you sometimes train models crazy models, and sometimes you discover a model that works better.
Though the maximal tree is on the training set, it is not on the validation set, right?
It is on the validation set. See, it lists the results both for validation and training set. This one, selection criteria, is the validation set misclassification rate.
Then initially you said that in the minimal tree node, in the case of growing tree, it does on training set, and in that other best classification, it does in the validation.
Did I say that? Well, let me clarify. When it splits, it always uses train. Yeah, when it prune, it always uses the validation set.
But pruning is used in best classification, right?
Yeah, both cases. Yeah. It's
Or in the maximum.
Yeah, so
It's not used.
it's not intuitive, but maximal tree does give you a more complex model. And it does seem to be worse, right? Here, this shows that there is a subtree that performs better than the maximal tree. So there should be another model that outperforms the maximal tree, right? But the result shows maximal tree is the best. Yeah. I would suspect did I specify the right assessment? Misclassification. classification. I think well, to answer that question thoroughly, I need to look into it. It is a surprise, at least from the result, right? Maximal tree is expected to be worse than best classification tree, but somehow here it's better than the best classification tree. Yeah, I think I need to look into it. Any others?
From my result right here, the best algorithm is for the best classification tree.
So your result is different.
Yeah, it's different than.
What's your error? What's your error rate?
You mean the mean square error?
The what? Did you select the mean square error?
No.
Uh,
What did you add?
Do you have the same column name as here?
Yeah, and the best classification tree is 0.423633.
Okay, so yours is better than this result.
Yeah.
Right.
And the bottom one is 0.424407.
So that's the same. So somehow you have a better result here for the best classification tree. Maybe because some of these settings could be, yeah. Maybe we can talk more after the class. Let me find out if we have the same settings or what different do we have that, produce a different model. Other than this, what other questions do you have? Good?
I have one related to the homework.
Right.
In the homework, it says create a full set of the rules, like generate a table.
Mm-hmm.
Do you do that within the interactive decision tree, or do you make a new node to generate a table?
Well, that is the one I was talking about, a lot of information, and it was analyzing different nodes and the if-else condition, and then the confidence and the cases. That's where you will get the information. It doesn't matter if you use the interactive or if you don't use the interactive. Do you know where to get that information? After you have trained the tree.
I can only do it per node. It wants a full set, but I can only get it per node. So I don't know if I'm supposed to.
Well, that's
create a
not.
table.
Well, you can get the full set.
Oh.
You should be able to get the full set. After this class, you may want to review the video, the first half. Any other questions? Great. So I'll talk about regressions. We'll just talk about it because I assume you have more knowledge, experience with regressions. So, we'll talk about, the key terms there. I will make sure that everybody is on the same page. Then we can fast forward things. We don't have to talk about regression like it's a new thing. All right. For that, I will pause the record. So here, the target variable is donation. So the regression models will be logistic regression, and it will be selected. It will be automatically selected as logistic regression when you drag the regression node. SAS makes that decision based on the target variable, so you don't have to change it. I think before that, we need to do two things. One is the missing value imputation. For regression models, you need to impute the missing values in order to use those cases that has a missing for the particular variable you want to use. Another thing you need to use is standardizing the variables. So you know how to standardize a variable using z-score standardization. Now let's do the imputation here. So I think it's the first exercise on chapter 4, regression models. Regression. Okay. So, if we take a look at the data set, so this one has a lot of missing values, but this is the rejected another target we're not using, so that would be fine. If you observe some of these variables, gift count, average, card, 36 months, you do see a substantial amount of missing values here. So to be able to use all the data points and still use this variable, it will be necessary to deal with the missing. Now we can exit. So the idea is to do a regression here, but before that we will deal with the missing, and we'll deal with the standardization. The imputation will be under modify. Right. There's a default method that will be applied automatically to all the missing values depending on the type of variable. Let's see. For class variable, class input, which is nominal input variables, we would recommend a tree-based model, which will run a small decision tree in the back and try to predict the missing value, the best case scenario for the missing value, using a decision tree. So that would be better than, you did the homework. There are alternatives to replace the missing. You can throw it away, which is not good. You can use a fixed number, which is arbitrary. You can use a mean or mode, which is good, but sometimes it's not the most typical case. Median is always better than mean for interval variables, and a best approach would be imputation, right? So sort of model-based imputation. Using a tree would be a model-based imputation for the nominal variables. Right. Normalized values. Whether to use the normalized values. That should be fine. For the interval variables, the mean is the default method. At least for this, you would like to change it to median. Always that would be preferred for the interval. And after that, we need to specifically choose variables inside. Also, there's an option here to create indicator variable for any missing status. So what does that mean? And you can choose different types. You can choose single or unique. What it means, basically, the indicator variable is to document, using an additional variable to document whether or not imputation was done to a particular case. So if I'm one of the consumer in the data set, I don't have any missing values, then this additional variable for me will take a value of 0 because no missing was done to me. In alternative scenario, if I had a missing value, my age was missing in the data set, but then my age was imputed by one of the algorithms, then this additional variable, indicator variable for me would be 1. That means I originally had a missing value, but then the missing value was imputed by some kind of algorithm. So this indicates the status of missing originally, right? Why is that important? Because sometimes knowing that the information is missing for a particular case is by itself informative. If the missing trend is systematic, right? This depends on the context then. So let's see, if I do a consumer purchase study and I want to predict the likelihood of purchase, then I do a survey, ask people about their income. And then low income people will be reluctant to indicate the income, maybe. And then I will have a missing value for that, for those part of the respondents. And then the missing status itself may indicate that they have a lower likelihood of purchasing because of lower income. So that's one example. So this gives you some additional ways to model the relationship between the missing status and the target. So this creates this possibility. If you say none, then nothing will be created. If you choose one of these, then additional variables will be created. The single one means only one missing indicator will be created for any number of missing imputations done. The other is simply to create one additional for every additional imputation that's done. So this is something to know. So this might be something that you should try when you do the projects, when you do the group project or single project, when you have done all the standard models, but you want to creatively make some more additional models. This is something you can try, right? To create additional variable and see if that, increase the performance of the model. I think that's it. So by simply doing this, it helps you to use additional cases from the data where there were missing values. After the imputation, you can use those cases. Only 2 variables had missing values. After imputation, the original variables were rejected, right? And the new variable has this label. Both of them are interval variables, so the median was used to replace the missing. So that's the result. Then you also need to standardize, and standardization is in transform variable node, right? If you remember, to do standardization, you will use the transform variable node. The tutorial also talked about log transformation. That is something unique. Log transformation fixes the skewness, as I talked about in second class. It removes the skewness to some extent and may help you may help regression model better capture the linear relationship, but sometimes it may worsen the model because the nature of the relationship the linear relationship was really on the original scale, but not on the logged scale. So when you log transform the variable, the linear relationship may decrease. So it's a mixed story. It doesn't guarantee you any better. Log transformation is recommended for statistical analysis, just because log transformation evens out the error distributions, and it helps the data better conform to the assumption of the regression. But so that's for statistical purposes. But we're dealing with prediction. Anything that improves the model, prediction would be better. So, the utility of log transformation is mixed. I can't recommend it. I can't say no. So you need to try, right? To log transform variables, it's the same place where you do the standardization, right? It's the transform variable node. So I won't do it here. I'll simply do two regression models. So I'll do a forward selection. Let's see. Or maybe I do a full regression where I include all the input, and then I do another stepwise regression which has some variable selection mechanisms. So this is full regression. Main effects, two factor. You can also add polynomial terms, but I will not do it here. This is somewhere you can try to explore additional models and try to improve the performance. And it says regression here because it detected. And sometimes even if your target variable is interval, like say, price, sales price, and when you do the regression, it shows logistic regression. Don't worry, it will not misapply the type of regression. It's simply because it didn't run or maybe it didn't update. But back in the analysis, it will use the right type of regression. Suppress intercept, no. Selection, model selection, variable selection mechanism. For this one, I'm not using any selection. I'm using the full regression model. Let's see. So that's that's a full regression. Another regression with some selection. In stepwise regression, I would choose model selection to stepwise, and keep all the other selections. And in this case, I will link it to model comparison, and compare all the models together. So in this case, the stepwise regression seems to perform better when it uses a combination of forward and backward selection. So this mechanism help it to retain the most important variables and remove least important variables. So in this case, see if your results will be similar to mine. Full regression is even worse than the maximal tree. So if your best classification tree had a better result, then the full regression would be the worst model here in terms of validation misclassification rate. So the full regression, it does harm the prediction of the model by including everything in it. So you want to have some selection mechanism to avoid including everything in it, right? Because this data set does have 30 plus variables. It's quite a long list of variables. Well, maybe next time I'll talk about the homework of regression. Okay. All right. So that's it.